Good afternoon, good morning, because we have some people in different time zones. We are very glad to have you here in our fifth AMOZONE webinar. So this is a continuation of a whole series of webinars we have been doing with many participants. And also today we have over 100 people signed up for this webinar. It's a mixture of, it's a nice audience, a mixture of end users, for example, a lot of utilities from across the world working on drinking water, wastewater, reuse. Consultants, technology companies are present. So yeah, welcome to all of you. So the topic of today is how to use AMOZONE. So this model we have been developing throughout the years for rapid virtual piloting, effective process design of ozonation processes, and also smart operation and training. We have a lot of content for you today, so we decided to go rather broad to give you a very good overview of what is possible, rather than going very technical and very deep. But of course, we are very open to go very technical with you in separate meetings or also in the Q&A of this webinar. So what are the formats and the objectives of today's webinar? So the context is the emerging needs in the water industry. So I'm personally now in the water industry for 12 years. It's not that long if you compare it to some other experienced people. But I have seen so many changes, and never before, I think, if you go to an event right now, there have been so many changes at once. We are talking about water scarcity, climate change, all of these things. So this is emerging, and actually the role of ozonation is also changing, because this is a technology that is very old. It exists for over 1 century. It was invented in France, and it's still emerging today. What are the objectives today? You get new insights that have really practical value and relevance to you. You also understand the practical application of using computer models to virtually assess processes, to better design plants, and to also smartly operate them. And our attention was also to look a bit over the walls of the water industry. This means we have a mixture here of drinking water people, wastewater people, and also people involved in water reuse or multiple of those domains. And the purpose is really to look higher level, because there are so many similarities and we can learn from each other, definitely when it comes to ozonation. The format of today is a hybrid presentation. So it's a presentation with live questions and answers. We also have some polls in between. If you want to ask questions, which we really stimulate you to do, please use the Q&A. So if you hover over your screen, you will see a Q&A button. Please use that to pose your questions, and we will answer them live if they are relevant to the content. After the webinar, there will be a short questionnaire. Please fill that in. It really is important to us because we want to continuously improve these webinars. There will also be an email, a follow-up email with this questionnaire. Good. So the content of today, this is the menu. It's dense. So 1 hour, you're all busy people. So we wanted to make optimal use of your time, but this also means you will probably have to be sharp because there's a lot of content coming. The first topic is the trends and the challenges when it comes to ozonation. Then we will go to the most interesting part of this webinar, which is the case studies and live demos. We will go over 3 big parts: virtual piloting in planning stage, virtual design, so designing a new ozonation plant, and operating them smartly with digital twins. So that's the part number 3. We will end with some conclusions. So this is the webinar team. I am Wim Oudenaert. I'm co-founder and CEO at AM Team. And actually, I did my PhD on this topic more than a decade ago. So it's still a topic close to my heart. We have Roberta Muyo as well attending from Italy. Roberta is project manager and simulation engineer at the AM Team, and she actually has been modeling a lot of ozonation plants at a global scale. Same for Giacomo. So our colleague Giacomo, he's senior simulation engineer, and he has been a very big driving force behind the development of AMOZONE, and he also worked for numerous customers worldwide. Then we have Peter. He's not in the webinar today, but he helped setting it up, a senior solution engineer and working with a lot of our customers. Same for Anna, also solution engineer at the AM Team. So this is the webinar team of today. Good, a short introduction of AM Team, because it's important that you know who we are, why are we doing this webinar. Well, we are a company that builds computer models to help tackling water industry's biggest challenges. One of them is water reuse, for example. That's where you will use ozonation. Another one is micropollutants. Another one is greenhouse gas emissions. Another one is making optimal use of existing infrastructure. So we have a lot of challenges. And we work for water use, drinking water, wastewater, and we build computer models for the treatment sites. So from primary to advanced tertiary treatment, everything in between, we have been working for a lot of customers to tackle specific challenges. And of course, this is part of a whole digitalization journey, using computer models to do new kind of things. We are headquartered in Belgium, but we have a global reach. As you can see on this world map, these are a couple of our regions where we are active in, where we have active ongoing projects. So it's quite global because we are quite specialized. And what makes it a little bit special is this combination of cutting-edge simulation capabilities with process understanding, because we believe you can only build a very good computer model if you really understand the process. Some of the customers are on our slide here. I'm sure you know a lot of them. So a lot of end users, for example, a lot of utilities, as you can see here. But we also work with industrial end users, a very big industrial end user with specific facilities. We also work with engineering and consulting firms. So this is also rapidly growing, and a lot with technology companies as well. So we help all of those applying models to come to optimal processes as fast as possible. We use different kind of tools, but the main ones are CFD, computational fluid dynamics. But we have actually applied that for quite new applications. Yeah, so we use multiple phases, as it's called, mixtures of water, gas, and particles. For example, ozonation is a two-phase process. You have water and you have some bubbles. Yeah, this is based on physics, and you literally get nice 3D visuals of your process. Is it mixing well? Is it doing well? Can we optimize that? And you can use that model to redesign the process. But kinetics are also very important because in the water industry, we do things, right? So by either biologically, physically, or chemically, things are being converted. So we have been building or applying different models. For example, at the wastewater side, a lot of biokinetic models, but we also have been applying a lot of chemical models. And in the drinking water side, also different ones next to oxidation processes. Yeah. Okay, so this is, and we use the combination of both because that's very powerful. And this is one of the topics in this webinar. So you will see a lot of examples. Good, this brings us to the trends and the challenges when it comes to ozonation. What are very big trends in the water industry? Well, we have split them up in these three very big areas. We know there is also process water, like industrial water, but let's limit it to those three. So let's start with drinking water production. Well, there are new sources being used. We know multiple utilities right now that used to be 100% groundwater companies, and now they are looking into starting to use surface water as a drinking water source. A very big shift, because everybody knows these treatment trains are very, very different. The dynamics are very different. There are also new target chemicals to be removed, and also many of the plants have capacity changes, increase, decrease, or are facing retrofits. So these are quite some challenges there. When you look at indirect or direct potable reuse, ozone plus maybe activated carbon adsorption is becoming a new gold standard. This means in the past it was all membranes, RO, very tough, let's say, or very strict multiple barrier concepts. Well, ozone is really emerging. Look at SWIFT, for example. SWIFT is a project in Virginia by HRSD, one of the biggest reuse projects in the world that is ozone-based. And these are some pictures of the current research facility. One big example, but look at California, a state in the US that is very hard on water use. They're also looking into ozone. Big shift there. And then at the wastewater side, the biggest topic over there is micropollutant removal. Look what happens right now with the revision of the Urban Wastewater Treatment Directive. It is literally for the first time ever stating that plants above a certain level will need to remove micropollutants. So this is really a work of, let's say, 2 decades to get it into the regulation. Big shifts. So this is the first poll, and you will normally see it on the screen right now. So what application domain of ozone or multiple of them, are you most active in? What is most relevant to you? So votes are coming in. I already see we have a nice mix of people here. Okay. So let's give it 5 more seconds. Yeah, for your votes. Okay, let's bring up the vote. I will now share the results. So normally you should be able to see the results right now. It's nicely mixed, right? So we have many people working on drinking water, 1/3 or something more on wastewater, and then also water reuse. So thanks for the votes, a very interesting mixture of people. Okay, so let's continue. What are the challenges when it comes to implementing or operating an ozonation process? Well, there are 4 big ones, more of them, but 4 big ones that come to our mind immediately. They were tackled in our previous webinars in detail, so you can definitely look at the recordings. The first one is every water matrix is unique. This means every design, every operational strategy for each site will also be unique. It's a mixture of chemicals, and how ozone behaves or performs in a certain water matrix at a certain plant is really driven by the matrix. Second challenge is lab or pilot testing takes quite long. It can really take up to multiple years. It is quite expensive, but the problem is a bit that it leaves many questions still unanswered when it comes to design. So that's a second challenge we have defined in the industry. A third one is design is a balancing act because you have costs, operational costs or investments, but then you have the performance. Okay, what is my disinfection, my CT, or what is the removal of my micropollutants? But then you also have your byproducts. Specifically, we are targeting bromate here. So you really have to balance all of those things together. And finally, in the end, the key variables that are hard, the key variables that you are really interested in are hard and expensive to measure. For example, up until today, there is not a good sensor for bromates online. There is also no sensor that will tell you in real time what is your removal performance of your micropollutants, for example. So these are quite some challenges. So this is why we have been building AMOZONE, which is a process model that contains a lot of chemistry. You can see that here. This is very complex. We will not go into very detail, but all these equations are in there. So it's a mechanistic model, not a data-driven model. But the front end looks a bit more simple. It is a virtual plant that is displayed here, and it gives you some outputs as function of time or averages. Yeah, for example, in this case, bromate. We were glad to win the Water Europe Innovation Award 2021 with this model because Europe stressed the importance for also in the framework of new regulation. Now, we started applying it commercially 5 years ago. Where is it now being applied? So that's the big question. Well, the first one is in the planning or exploration phase. So we do look at technology selection and feasibility. In this stage, we call this virtual piloting. So we are in this stage completely or partially replacing on-site piloting by computer simulation. And in this case, the questions you have is performance, feasibility, the costs of such a potential future plants. Yeah. Then once the decision is taken and people go into the design stage, we help applying the model in conceptual and this detailed design to really have a well-functioning process, because fixing a reactor design once it's built is very difficult. So here the key questions are, what is the dimensions needed? What is the design? And detailed design can literally mean, where do I put my diffusers? Should we move a baffle wall? It can be really detailed. And then once it's built and it goes into operation, new questions arise, and we use the same model for smart operation and training. Training is very important as well. We have seen that, especially if you're new to ozone, but this is called the digital twin application. So a model that predicts what you cannot measure based on what you can measure for real-time monitoring or what-if testing. So here is the next question. on a poll. So which stage describes most your situation when it comes to ozonation? So either you're exploring or planning, you are in design stage, you are building a plant right now, or you're already operating one or multiple ozonation plants. Okay, let's give it 5 more seconds. And here are the results of the poll. All right, I will be sharing them now. So most of you, almost half, are in exploration planning stage. Very good moment to follow this webinar, I would say. So in that stage, you really want to learn a lot at a fast pace, what is being done at other sites. People are also in design stage, 20%, and some people are constructing, and a nice percentage is also operating already. So there is quite some experience in this audience already. So this is very promising for the Q&A. Good. Now we come to the most interesting part, the case studies. Let's introduce them a little bit. We have selected a few because we can, we have to limit a little bit that it's a good mixture. We have decided to make a mixture between virtual piloting, design, and also digital twins. So we have one plant from Sweden that we helped developing together with Sweco. So we did a virtual piloting for that plant, wastewater. So these are these brown droplets. If you see them appearing in the webinar, these are wastewater related cases. The blue ones are drinking water related, okay? Then we have another one in the Netherlands where we first did the virtual piloting in 2021. We helped the design in 2022 and currently /23, and currently we are building the digital twin. Yeah, so this is a plant going through all of the stages. We have a plant from the Netherlands, another one, a drinking water treatment plant, where we are mainly focusing on the digital twin. And then we have a French case where we will be focusing on design and also a digital twin, and another French case on design or a redesign. So this is the mixture of today. So I will hand over the microphone right now to my colleague Giacomo, and he will be introducing the virtual piloting part. Giacomo, the floor is yours.
Thank you. All right, so we'll go through the typical workflow of a virtual piloting exercise. What we typically start from is a real sample, real data that we feed into a virtual representation of the plant, simulating an ozonation plant that takes the effluent of a wastewater treatment plant or any other stream, and then we run simulations and we mimic what would happen if we apply an ozone dose in terms of micropollutants removal or bromate formation. We can test a large number of scenarios, and normally in the feasibility study, in the technology assessment stage, we run in a few weeks a huge number of scenarios. Now, when the data are available, then we feed the model with fixed steady state conditions or dynamic conditions, and the model, the mechanistic model is behind this what we call the virtual installation. What we see in front of you, it's really the virtual pilot plant in which the flow, the water matrix goes in through bubble columns, in which the ozone dose can be delivered. It can be designed in many ways in accordance with the client, and then the ozone dose can be delivered with many strategies like flow proportional, DOC proportional, and many others. So in this specific example was a water matrix from an effluent of a municipal treatment plant in Sweden, in which we tested, we calibrated the model on standardized ozonation test together with the experimental data, and then we ran the model in the virtual pilot installation in different doses of ozone, and injecting the ozone in multiple points of the installations, because distributing the dose has an effect on the micropollutants removal, but mostly on the bromate formation, and in different conditions, and maximum flow, minimum flow, also having specific composition of the water, because when a rain event hits a plant, then the water composition changes. What you can see here in a nutshell, without going into much detail, is that the highest scenario, the highest dosage of ozone gives, if it's dosed in one column, then it gives the highest local ozone concentration, which are then depleted along the installation, right? When we explore the same dose at the maximum flow, but across 3 injection points, the local ozone concentration is distributed across the whole installation, across multiple points, and then you locally reduce the amount of ozone in the liquid. And what is also one interesting point of view in terms of assessing the size of the generator, doing an initial assessment is also to establish the size of the generator that we would need for such a control strategy. Then beside this, we also look in terms of bromate, what happens, and micropollutants removal. But in this case, you see the bromate results for each of these scenarios, and how a very high ozone dosage would bring a too high bromate formation. And then there are more, let's say, smarter ways of distributing the same dose, or achieving the same micropollutants removal with a lower dose, and allowing us to minimize the bromate at very, very low values. Now, I will take a moment, and I will hand the mic to Roberta for the live demo. Thank you.
Yes, thanks, Giacomo. All right, so now what we are looking is a real-time dynamic simulation in our virtual environment. So what you can see here is a virtual pilot of a secondary effluent ozonation plant. Ozone dose is injected in these first 2 bubble columns, first 2 units, and then we let the ozone interact and be in contact with the water in the remaining units. So here we are currently running a dynamic simulation. Here you see the influent flow rate in blue. You can see that there is a combination of dry weather condition and rain weather condition, especially in between day 3 and 4. We have a heavy rain event. And together with that, we can also look at the dynamics of the water metric composition. For example, in green, we can see the dynamics of the DOC concentration with a peak just before when the rain event starts, followed by a lower concentration, so a dilution during and after the rain event. Similarly, the ammonia concentration with an increase just at the beginning of the rain event, and big dilution with value close to 0 during and after the rain event, and then average concentration. Now we're running a simulation with a PID controller, which means it's a DOC proportional controller with a set point of 0.5. So the ozone to DOC ratio is 0.5. And then we can look at some effluent concentration, effluent variables in terms of ozone residual, making sure that all the ozone is being depleted and is consumed before it it get discharged. And we can also look at bromate formation, for example. Here in the bromate formation, we see some particular and interesting dynamics. So we have like a baseline concentration, which is very low, around 0.2 micrograms per liter, with some peaks. And especially in the rain event, we see an increase of bromate. First of all, we can ask ourselves the question why we have this increase in bromate during the dry weather condition. And we can find an answer if we look deeper into the ammonia dynamics. You can see that in certain moments of the day, the ammonia concentration goes very low. And we know that ammonia has an important role in the bromate formation chain, because if ammonia is present, it can sequester the isobromous acid to form bromamines and preventing the bromate to be formed. So when ammonia is lacking, then bromate peaks can appear. And this is even more pronounced during the rain weather condition, not only due to ammonia, but also due to the certain particular behavior that happens during the rain weather condition in terms of radicals. So here we're looking at micropollutants removal, average removal along the dynamic removal, actually along the days, along the time, and we can have very fast removing compound and low reactive compound that are hardly removed. What is interesting to see here is that during the rain event, we have an increase of micropollutants removal. Why? Because with the dilution of the water, the scavenging of the radicals is less pronounced, which means that we have more production of hydroxyl radicals, leading to higher micropollutants removal and, as we can see, higher bromate formation as well. So with this fast and dynamic simulation, we can already think of possible improvement in the operation, so possible smart dosing strategy between rain and dry weather condition. And with that, I'll hand it over to the presentation again.
Perfect, so Roberta, thanks for the demo. So if you have any questions, yeah, they are coming in. Great. Yeah, I was just going to say drop them in the Q&A, but it's already happening, which is very good. We will come to the Q&A very soon. So to end this section on virtual piloting, business case is very important. So if you look at on-site piloting versus virtual piloting, there are very big fundamental differences. Typically, the cost, what we see is in on-site piloting, if you want to do it longer term, it typically takes 100 to several hundreds of thousands of euros if you include man hours, renting or buying a pilot installation, analytical costs. So this is really the business case of a real customer, three full-scale plants in the Netherlands. And virtual piloting can lead to up to 90% cost saving. And typically where you are in the range of 80–90%, which is very, very significant there. Now, cost is not everything. Time also, because piloting really takes one or multiple years. It can take multiple months. It really depends on the scope, how broad you set it up. But typically it's significant. Only already starting it up, getting acquainted, troubleshooting, it already takes quite a while. While actually a full virtual piloting cycle is 1 to 2 months. You typically also have some issues on site, like experience issues or safety issues, which are not present in virtual piloting. And the questions that are typically unanswered after on-site piloting, we try to really answer with virtual piloting, because you can test all of these scenarios. So for example, this simulation Roberta has shown, you can really start doing a lot of what if scenarios. And this is what we are going to come back to in a demo of Giacomo on a drinking water digital twin. Okay, so we will be showing that. So good. So yeah, it's quite a big difference. And there are also hybrid modes. In some cases, our clients do a real piloting in combination with the virtual piloting. And then you can keep the one shorter, maybe complement the other and expand the information. So a lot of possibilities here. So let's go to the Q&A and see if there are any questions that came in. Okay. So maybe Giacomo, a question for you. Yeah, if you can come to the stage. So we have a question on the variables. Each micropollutant, is it really literally calculated independently in the model?
Correct. We call them state variables when they're independently calculated. And then each micropollutant, and now they're more than 70, around 100, something like this, are treated as a separate variable.
Yeah. And then coming also to the micropollutant still, which input do we use, for example? Do we let them change during a rain event? Or do these concentrations come in at a constant rate typically in the model?
Yeah, so that's a good question, and it relates to others that indeed refer to the type of input. The type of input can be dynamic or can be steady. It depends what is available and what is the objective of the study. The dynamic simulations can also include variable micropollutants concentration, and in particular, it's interesting to be included there, taking in consideration the effect of the biological plant. So the biomass and the biomass concentration variability will have an impact on the removal of some micropollutants, and thus on their concentration downstream that arrives at the ozonation plant.
Yeah. Okay. Thanks. So yeah, with regard to the dynamics, if you're working at the drinking water sites, you are way less faced with these dynamics. So let's say you can really see, let's say effluent ozonation as an extreme example of a dynamic ozonation system, if you look at it from that point of view. So dynamics also in micropollutants or fluctuations in DOC or rain, for example, is way less present in drinking water, where it's more consumption or production based. Good. Yeah, what input data, that's a final question of this section. What input data is used for bromate modeling, bromate prediction?
Yeah, so the bromate formation it's a very complex story. There are many state variables involved. There are many compounds, but in general, the bromide, the Br minus concentration is the most influential, the most important to know, as influent concentration into the plant that arrives. Then alkalinity, pH, all these other compounds have an effect. Ammonia, as we have seen from Roberta, has a role in the final bromate formation. So the more we know, the better, but we can also make assumptions based on the geographical location and type of water. Yeah.
Okay. All right. Good. So more questions, definitely welcome. Just put them in the Q&A. We will come back to another Q&A section later. Perfect. So yeah, that's to summarize that a bit. That's the difference between a data-driven model and a mechanistic model. We try to put in a lot of chemistry in the AMOZONE model, which means that if we go to a new plant with a very limited effort or very limited new data, we can have the model up and running. That's really the core philosophy, let's say, behind this methodology. This brings us to the design. So when you go through the virtual piloting stage or your pre-research, let's say, and you decide, okay, let's go for ozone, the design thing starts, the design process, let's say. And this is a process where a colleague, Roberta, will go a bit deeper on, and she will be sharing a lot of case examples here.
Yes, thanks, Wim. So indeed, before diving into the detailed design question and case example, let's first ask the question, what are the main challenges when it comes to design an ozone installation, be it for drinking water application or wastewater application. There are 4 main drivers, which are summarized in this slide. First, the human factor, which we cannot influence a lot. So we'll, in the course of the presentation, we'll focus on the remaining 3. First of all, we have the water metric. The water metric characteristics is very crucial. It's site-specific, case-specific, and the type of organic change from water to water, and seasonal variability, etc. This is very important because it drives the consumption of ozone and ultimately the performance of your installation in terms of average removal of micropollutants or in terms of effectiveness of the disinfection for drinking water purposes. Next to that, we have the system design. So really, how would you design your ozone installation? Where would you place the baffle or the diffusers and so on? And finally, the process parameters. With water metrics properties that you have and the system design that you have, then how would you smartly operate your installation? Where would you distribute the dose, for example, these kind of things. So with the combination of CFD and AMOZONE kinetic model, we can actually address all of these 3 main drivers. And we can actually adapt this the design based on the specific water matrix and the process operation. So this is a first case example in France. It's a project in collaboration with Veolia, where we helped and support the design stage of a new-to-build ozonation reactor for disinfection. So here on the left, you see the original design with some inlet and outlet and the baffling factor baffling configuration. And the main question here, the main goal was to optimize this design, this original configuration for maximize the disinfection, so the contact time, and minimize the bromate. So here on the right now, you see a picture, an image of bromate concentration displayed in 2 cross sections in the reactor. And blue means low concentration and red means high concentration, so a bromate hotspot. As you can see in this original design configuration, there is a preferential flow occurring, which will compromise the CT because you have a not even distribution of your ozone in the reactor, and also leading to hotspot of bromate formation on one side of the reactor with this red hotspot. Then how did we tackle this? We had many degrees of freedom. We could act on the design, on the changing the inlet distribution, diffuser placement, etc. And after running several design simulation, we could finalize an optimized design configuration where basically with the same CT, so with the same contact time, we could minimize the bromate formation significantly. Now we can switch actually to wastewater secondary effluent application for micropollutants removal in the Netherlands. So this we have already seen in the previous section, the virtual piloting stage, which we have done together with water utility De Dongo. Now, together with the building team, the BOW team, we have also developed the detailed full-scale design of the ozone installation for micropollutants removal. So the goal is to have an average removal of micropollutants 70% while maintaining a minimum bromate formation. So also there we could test several design configuration, and here we're presenting 2 configuration, 2 completely different actually design concept, a counter-current concept and a co-current concept configuration. And we could also observe very different results in terms of micropollutants removal. So the co-current configuration, thanks to enhanced performances, is able to remove micropollutants better. So we have higher micropollutants removal with the same dose, and also leading to a similar bromide formation, also very important to mention. And then this brings us to the final example of the design stage. We go back to France and to a disinfection ozone reactor. Here it's a different case because it's a revamping of an existing ozone installation. So there's an existing design where we want to maximize the performances, so maximizing the disinfection capabilities while minimizing or maintaining the bromide formation as low as possible. So on the left side, you see the existing design, and on the right side, you see the optimized design. Also there, we could act with several, including several baffles, increasing the reaction, ozone reaction chambers, and so on. And now we see a summary of the outcomes of this interesting project, where we are basically comparing in this slide the existing design and the optimized design in terms of bromide and ozone residual concentration. So first of all, if we look at the bromide, we see that with the same dose, so we're comparing two cases under the same ozone dose, we can have a similar, very similar bromide formation. So the bromide formation is the same, but we have a different ozone residual distribution along the reactor, thanks to different design configuration. And now if we look at the bottom graph, we can see that in the optimized design, we can have much better, higher CT, so contact time, compared to the existing design. So actually, this means a lot of dose saving to meet the minimum CT in winter and summer conditions.
Okay, thanks, Roberta. So if there are any questions on this design section, let us know in the Q&A, so we can definitely go on to a couple of questions now. Yeah, maybe Roberta, a question for you. So does the model include the different behavior of micropollutants? For example, you have chemicals that react very fast with ozone and very slowly. How does the model take this into account?
Yeah, that's a very good question indeed. The question is yes, so the model can take into account the different sensitivity of a specific micropollutants to ozone and radicals. So basically, being a mechanistic model, each micropollutant has its own reaction constant to ozone and radicals based on literature. So there's a lot of literature and bibliography available to where to find this constant rate. And based on that, we can predict the removal of that specific micropollutant and the sensitivity to ozone and radical.
Okay, thank you. So related to that, there was also a question on transformation products. And that's a question we sometimes get at. Do you also predict the transformation products? Because of course, when you oxidize something, you get some other products. Now, we can do that. There are pathways known, and it's very easy for us to include them. But right now we have been focusing on where the priority lies, and that is on the parent components. Because yeah, regulation was, for example, if you look at the wastewater sites or in general, regulation was already very premature when you look at general chemicals. But the next stage definitely is to include more of these, because we get the question more and more. Yeah, okay, good, perfect. Another Q&A question will be coming. So let's do another poll on the big questions. What are your biggest questions when it comes to ozonation? We hope to answer a couple of them in this webinar, at least partially. Let's see. So byproducts, process efficiency, performance, learning about your new technology at a reasonable pace, or other. So what are the biggest challenges? So votes are coming in. Okay, let's end the poll and look at the results. Okay, you should be seeing the results right now. So interesting to see is that process efficiency and process performance are the major concerns. They are the main concerns. Byproducts are a bit less in this general audience. What we have typically see, if you look at bromate, for example, is very specific, very country or site specific. And then there can be a huge concern. And then at other sites, there is no concern at all. But efficiency, process performance are very important topics. Okay, thanks for voting. Perfect. So let's continue a bit with the part number 4, the digital twins. Yeah. So this means using a model. So we actually use the same model as we use maybe in the virtual piloting, virtual process design. Now we recycle, let's say, the model, transform it a little bit in a fast version to be used in the operational stage for smart operation. So this is the topic of digital twins. And yeah, I think, I know, I will shortly introduce this and then I will give the word to my colleague. So what is a digital twin of an ozonation process? To our understanding, how we define it typically is it's a bunch of mathematical equations. We don't care how they look like, but it's some magic, let's say, in mathematics that gives you variables or insights you cannot measure based on what you can measure. For example, when you look at ozonation, just imagine you would have a digital twin that predicts in real time your bromate, the removal of your target contaminants, for example, a set of 10 or 11 or 5 chemicals of interest. That would be of value because you cannot measure them in real time, but the operation depends on it. So this is really smart and proactive operation. But on top of that, you can also use the model offline for additional what-if testing. Now, what we also saw is that it leads to accelerated training in terms of a flight simulator. So we literally have customers that start playing with the model themselves to really accelerate the learning and the process understanding. Yeah, so you have actually a flight simulator at your disposal. So Giacomo, now you can elaborate a bit more on this topic.
There we go. Thank you. And what you see here is the conceptual workflow that brings from a very highly detailed CFD plus kinetic simulations toward a dynamic simulation. So the workflow that brings the CFD insights in terms of hydraulics and mechanistic knowledge in terms of chemistry into a simplified version of the same model, which can be run online. So in parallel with the installation, or even faster, faster than the installation, can run quickly very long simulations to test what would be the best action that we take operationally to drive, to steer better the installation. So in the, I forgot something to mention about the slide before. This is the project that you have seen across the whole presentation. This is actually currently the last stage in which we're exploring with the Waterscape Domo the design of their actual digital twins, so that Roberta just mentioned. So in the next slide, instead, you will see, in this case, a drinking water installation in which an advanced oxidation process is taking place. So this is all included in the AMOZONE, right? And the AMOZONE was implemented in this installation, in which the water gets in, it gets treated with ozone plus peroxide, so peroxone process, and then the water follows to the next treatment, which is a UV treatment, in which UV peroxide to the final treatment and removal of the micropollutants. Now, what you see in the graph below is measured data, and the yellow line is the simulated very long time series across years of experimenting with the installation. So that's how the model performed through this data, thanks to the influent information into the influent dynamics, which we could use to to run case scenarios or design controllers, just like in this case. So in the yellow lines, you see the actual operation, how the installation was operating in these years. And with the model, we could run advanced controller situations with virtual controllers that would have suggested in this point a better combination of ozone and UV dosing. So balancing the UV power, so saving power because it's more expensive than generating ozone, and limiting the bromate formation. So maximizing the micropollutants removal and at the same time having a good quality effluent water with minimal operational costs. Of course, the micropollutants picture is important, and all the micropollutants of interest were monitored in these simulations, making sure, and that's the controller action, the controller's objective, making sure that the target removal, what the utility has to comply with, as the average conversion is maintained. Now, I will take over control of the screen, share my screen, and guide you to a live demo. What you can see here is a drinking water installation in which an effluent is flowing through the bubble column 1, and then bubble column 2, and the final bubble column 3. So in this installation, we are now injecting a fixed 1 milligrams per liter dose into the water. You see the controller takes action. We can check the dose from here. So we are at 0.9. So the controller is increasing the dose. And at the same time, the flow is changing. So there is a dynamic flow coming in. So the controller has to adjust in real time the delivered dose, right? So at a certain point, we can have a look at the ozone residuals, how they are. And since it's a drinking water installation, it's very important to minimize bromate and also maintain the required CT. So we see that the CT is fluctuating quite a lot. Then what we can do to reduce bromate is to switch on the other two bubble columns, spread the same dose across multiple points of the across the whole installation, and then continue with dosing. Now the gas flow, it's like switching on the gas flow in bubble column 2 and 3, right? So for a moment we have an overdosing of ozone, and then the controller starts acting on the bubble columns. The gas flow goes down, and then we are aiming for the overall 1 milligrams per liter ozone dose. The ozone residuals decrease again. They go back to normal values, and now the bromate will decrease even further than what it was before, because we are spreading the dose on a bigger volume, and then still the controller will keep on balancing with the effluent flow. What happens to the CT is that it still varies because of but is maintained on a reasonable value for this installation for this time of the year. But what we can further do is to change controller and use an advanced one. So making the controller maintain a fixed CT value, for instance, of 1. In that case, that would be the optimal choice, because in the ozone dose will be minimized to have to maintain the target disinfection rate. And with this, I will give back the line to Wim, because I think we might be short in time at some point. Thank you.
Thank you, Giacomo, for the demo. Always nice to see these demos. Of course, I'm biased. I'm a simulation guy, but always good to see live simulations that are working and operating well. Good. So let's continue a little bit with Q&A. A general question, a very big question is, of course, validation and calibration of a model. So what we can do is group a little bit of questions, because we have had multiple ones, and we can group them a little bit and go a bit further to this slide, for example. So what we have done, of course, throughout the years is checking model accuracy. Yeah? This is very important. Because if you build a mechanistic model, that's what we typically do at AM Team. We build a lot of new models when we start applying them for the first time. These mechanistic models have to be calibrated and validated. And one of those examples here are a surface water plant and a secondary effluent plant, where you can see, for example, comparisons. We have many of those, but some simple comparisons of measurement data, always in green, versus prediction of the model. So, for example, this is bromate at the left in secondary effluent in a project in the US, Swift. And then we have bromates in a Dutch drinking water treatment plant. And at the right, you can see the target contaminants. And here you can see the different reactivities that are taken into account. So Giacomo, can you maybe elaborate a bit more yourself on the